Hi everyone, welcome back to Dynamics of Machinery class. Today we will discuss a problem on the topic of reciprocating mass, balancing of reciprocating mass or effect of partial balancing such as variation of tractive force, sewing couple and hammer flow. So let us see the problem. A two-cylinder uncoupled locomotive has inside cylinders 0.6 meter apart. The radius of each crank is 300 mm and are at right angles. The revolving mass per cylinder is 250 kg and the reciprocating mass per cylinder is 300 kg. The whole of the revolving and two-thirds of reciprocating masses are to be balanced, and the balanced masses are placed in the plane of rotation of the driving wheels at a radius of 0.8 meter. The driving wheels are 2 meter in diameter, 1.5 meter apart. If the speed of the engine is 80 km per hour, find the hammer blow, maximum variation in tractive effort and maximum sewing effort. It's a university repeated question. So first of all, thoroughly read the question. Two-cylinder uncoupled locomotive engine. Cylinders is 0.6 meter apart and radius is given 300 mm and both are right angles to each other. Revolving mass per cylinder, that means the mass attached to the crankshaft or maybe the mass imparted to the connection between connecting rod and crank, and 250 kilogram, and the reciprocating mass per cylinder is 300 kilogram. That means the mass associated with your piston is 300 kilogram, and we have to balance the whole of the revolving mass and 2/3 of reciprocating mass, and it's the plane of rotation of driving wheels at a radius 0.8 meter. That means we are placing a counter mass to balance the unbalancing. So there is a balanced masses are placed in the place of driving wheels at a radius of 0.8 meter. And again, it is important, it's an uncoupled locomotive, and find out the effect of partial balancing. So let us see the solution. Since the whole of rotating mass, that is m1, let us taken as 250 kilogram. 250 is the whole of rotating mass associated with the crankshaft, and 2/3 of reciprocating mass. 2/3 of reciprocating mass m2 is your mass associated with your piston, that is 300. It's 2/3 of 300 are to be balanced. So total balancing mass per cylinder is m1 plus cm2, that is 250 plus 2/3 of 300, that is 450 kilogram has to be balanced. That is the mass in our plane B or mass in plane C is 450 kilogram and at a radius of 0.3 meter. This is given in your question. The data is given in your question. To balance the above mass in cylinder B and C, we place a balancing mass or a counter mass in a plane A, which is MA, and a plane D, which is MD, at a radius of 0.8 meter at an angle of theta A and theta D from the first crank B. Take A as the reference plane. This is a common procedure for the problem. So let us draw a tabular column. First one is plane A, where the wheel A, and plane B is a for cylinder MB having a mass MB. Here a cylinder plane C having a cylinder mass MC. Since MB and MC are 450, we are found out, and we have to find out the value of MA, that is counter mass or balancing mass, which is placed in the plane of wheel A. Similarly, wheel D, the mass balancing mass is MD. Let us take reference plane is wheel A is taken as a reference plane, and similarly the radius we can find rod here 0.8 meter for the plane A and D, where we have to place our balancing mass, and the cylinder masses are placed at 0.3 meters apart or 300 mm. So we can find out MR. Next column is MR, that is the diagram to draw the details to draw the force polygon. 0.8 times MA, 450 into 0.3, 135. Similarly 135. Here 0.8 times MD. Here to draw MR is to draw our force polygon, but there is two unknowns, so we cannot proceed to first of all to draw a force polygon. Next one is distance from the reference plane. Reference plane is taken as wheel A, and distance from the reference plane to the plane A is 0, and similarly cylinder B is 0.45, 1.405, 1.5, and the MRL. This is the tabular column. Let us see how we will get the distance. First step, draw the plane diagram. That means the cylinder A, cylinder B and cylinder C is 0.6 meter apart. So first of all we will draw two cylinders 0.6 meter apart. Then wheel A and wheel D. Two wheels are 1.5 meter apart. So again 1.5 meter, the distance between A and D. We can find out the distance between B and C is 0.6. So this part will be 0.45 or the 0.9. The difference will be 1.5 minus 0.6. You will get 0.9. The half will be here. 0.45 from reference plane to cylinder B. Similarly, cylinder C to the plane D is 0.45. Next, space diagram. We know that the two cylinders are right angles to each other, and RB and RC are 0.3 meter. B and C masses are to be balanced is 450. We are find out that, and that is right angles to each other, and there will be a two unknown A and D. Next one is we can proceed. The distance is we got the distance from reference plane. Next you will get a column MRL. This is the column to draw our couple diagram or couple vector diagram. So this is here only one unknown, 1.2 MD is unknown. For balancing it should be a closed one. So let us draw for the first one. For the first mass MB or cylinder, the plane B, here the MRL value or polygon vector value is 60.75. So just make 6 centimeter in your scale, or you can take inconvenience with your paper. Draw horizontally 60.75. From here to here B to C, you can draw 141.5, 90 degree to this one, and so draw B to C another vector that is 14.1 centimeter or like that, with reference to your convenience scale. And the third side 1.2 MD should be a closed one. So just join O to C and measure 1.2. This will be your 1.2 MD, which you can measure in your scale. You will get 154.22 from your scale reading, convenient to your scale. So you can find out MD, you will get 128.52 kilogram, and you can measure the angle of OC, that is 247 degree. That means MD is 128.52 kilogram at an angle theta DC 247. Next we can find the value of 0.8 MD. So we will get a unknown in the force polygon, that is 0.8 times MD is 128.52. You will get 102.82. Next step, we can draw the force polygon. Same here, 135 and 135. So for the plane B, draw AOB with the convenience scale 135 and BC perpendicular to the here 135, and we got the value of OC, that is 247 degree. Draw the another vector, that is 102.82 in the plane of wheel D. Draw this vector CD, that is 102.82. That will be your 0.8 MD. So 0.8 MD you will get 102.82. The closing side will be the 0.8 MA. From your scale you can measure, which will be 1.82. That is 0.8 MA is 1.10.82, and MA you will get again same value 128.52 kilogram, but the angle is 203. Angle you can measure here from the point D, you will get 203. Now we find out the balancing masses MA and MD. Next step in your question, we have to find out what do you mean by what is the value of hammer blow and variation in tractive effort. This is the common procedure up to this point. To find out MA and MD is the common procedure in the previous problem. Now we will find out the hammer blow, but here there is an important point, that is 450 kilogram mass contain 2/3 of 300 kilogram. That is 450 kilogram mass contain 2 by 3rd of 300. That is 200 kilogram of reciprocating mass alone. As considering your hammer blow, we will take the part which is acting or which will impart to the reciprocating mass alone. So you just take the 2 by 3rd of 300, that is 200 kilogram of mass, reciprocating mass alone. Then we got 128.52 kilogram, that is balancing mass, which contain 200 divided by 450 into 128.57, that is 57.12 kilogram only corresponding to the reciprocating balancing mass. So this balancing mass 57.12 is the cause for the hammer blow. That is, capital B is 57.12 kilogram and small letter b, the radius is already given in your question, 0.8 meter. So speed of engine is 8 km per hour. You can convert 8 into 1000 divided by 3600, 22.22 meter per second. How we will convert kilogram meter per second to meter per second? That is 80 kilogram into 1000 divided by 3600. You will get 22.22 meter per second. Now the angular velocity or omega as v is equal to omega times radius. So angular velocity is equal to linear velocity divided by radius of wheel. Let us take here r is equal to capital M is given, that is 1 meter. So the angular velocity is 22.22 radian per second. Hammer blow is maximum hammer blow BB omega, the BB omega square. So BB omega square you will get 57.12 into 0.8 into 22.22. So you will get 22,561.4 Newton. This is hammer blow. Similarly, variation in tractive effort, you will use the equation plus or minus 0.2 1 minus C m2 r omega square. Please just by heart this equation, and here the maximum sewing couple plus or minus 1 by root 2 1 minus C m2 r omega square into L. This is a repeated university question. So maximum variation in tractive effect we can find out plus or minus root T 1 minus C m2 r omega square, where m2 is 300 kilogram, total reciprocating mass, radius is 0.3 and you will get to plus or minus 20,945 Newton, and maximum sewing couple. Similarly, L is the distance between, here is the L, the distance between the cylinder which is given 0.6 meter. Same value you can put here 300, that is total reciprocating mass. Here only the difference is that to find out hammer blow you have to find the what value, what the factor corresponding or contain 128.52 for the reciprocating mass alone. Okay, thank you.